Hello and welcome back. It has been quite some time since I last gave an update on where manifest development is. I am very pleased to say that this time was well spent inside of the framework's physics engine. Originally, I had planned to only update the contact detector, as previously demonstrated. It wasn't in the best of shape. However, as most things go, it was not so simple. All the major components, the integrator, detector, and resolver, all have been augmented. With the bulk of the work being done, I finally feel comfortable to begin sharing the progress as most of the development so far has been all or nothing. Today, I really just want to give an overview of what these physics updates are going to cover, as well as introduce the main topic at hand, which led to all of this, a collision detection pipeline. So as previously said, I'll just be covering the collision detection question at hand today. In the next video, I'll be covering the phases of collision detection as well as the tests that are used in Manifest. After that, I'll be covering the final phase in more detail and discussing how I implemented the test Dirk described at GDC 2015. And from there, it's undecided which order I'll do all these, but they will be covered. And this would be covering GJK in contact generation, SAT in contact generation, as well as resolving the contact points generated from all the collision tests that will be discussed. I will not explicitly be covering the integrator as it's really just moving some lines around. However, I will make sure to briefly touch on it when talking about the contact resolver. Alrighty, so let's jump into it. Our question is, how do we detect collisions, and really how do we build out a collision pipeline to efficiently detect and resolve collisions in real time? So let's start by giving a brief overview of your physics step. You're going to take your second order forces, turn them into your velocities. From there, you're going to do collision detection. From there, if we detected anything, we're going to do resolution. And then after resolution, or if there was no resolution, we just skip and move from integrating velocities to integrating position. And that's basically the anatomy of your physics loop. So how do we do these two steps? These are our main goal, and really detect is what we're focusing in on today. The first approach, and you can kind of eyeball it, there's only 5 objects here. Simply just check all the collision pairs and see, do we have any overlap? Obviously, that's not going to scale well. That running time will be O of n squared. And I don't typically try to be a running time person, but especially as we continue on and you see what some of these tests are and the complexity thereof, you're not going to want that. So ideally, we would like to go to something a little faster. And the way we can do that is with an acceleration structure. Now, there are many acceleration structures. In fact, you can even compose various acceleration structures to create your own for special purposes. But the one we're going to be using is a dynamic bounding volume hierarchy. And I won't be going over them specifically, but Aaron Cotto had a great GDC talk in 2019 that covers this. However, I am going to be using his kind of introduction to the problem and how it solves this um, to kind of get started. So basically, we can start by saying, here's our world, right? And we can make the observation that if we were to draw a line down it and then partition them into A and B, as long as nothing straddles this line here, anything on A can't intersect with B. And so let's, for right now, imagine we're in the process of detecting this collision right here. So we go through and we're on this hull and we're saying, all right, does the hull intersect B? No, it doesn't. So for now, we just get rid of it. There's nothing there anymore. And then what we could also say is, well, before we were doing this collision detection, we drew another line and we partitioned the world into A1 and into A2. And so again, we say, does this box collide with anything in A1? No? Okay. Just get rid of it altogether. We don't need to go any further. And then we continue this process until we essentially say, okay, we're in A2. This is in A2. That's fine. That checks out. And we go down and say these are both just base geometries. We have detected collision. And you can already see how after just two queries, we canceled out 60% of the work. We didn't have to go any further. And again, this is a very small count. It's only n of 5, so it doesn't really seem like that many savings, but you can kind of imagine in your normal game or simulation just how many objects there are. And when you create enough of these splits and manage them properly, you get very fast speed ups. And in fact, you go from O(n) squared to O of log n. And that is very permissible. We are okay with that. So how do we do this though? That is the main question. This is great, but how do we actually accomplish this? Let's just assume. I'll put this back up. Let's just assume we have our dynamic BVHs. Well, we still have to turn this into code. So one solution, and this solution is going to take us far, but it's going to have some problems. And it's actually the one I tried at first, which is just inheritance. Good old C++ inheritance. So if you're like me and enjoy pattern matching games, this example will speak to you. But inheritance can kind of be thought of like this. Say we have some struct A, and it looks like this. Some horrible programmer art star. And then we have some struct B, and B, just a little circle. So what we can say is that A, pictographically, looks like that. It's a little star. But if B ends up inheriting from A, we would say B is not only the circle, but it's also the star. And so this is kind of a good way to think of C++ inheritance. We take our object and then we just add everything else into it. And we can kind of see why this helps us out if we kind of plot out this world. Let's actually bring it back. So if we go ahead and try and actually build out this BVH over here, what we'll see is we end up with something kind of like this, where we have the main bounding volume of the world. Then here's our little split. And then we have these two objects over here. And because it's a binary tree, you're going to end up with container wrapping those two. And with these objects, it's going to have its split. And then we're going to have our actual collision down here. And these two will be wrapped up. Now, this is actually a lie, because we don't really have this. What we really have are little extra boxes that go around our geometry. And for the sake of visuals, I'm not going to go too much further, but you can kind of get the picture. We don't really have this. What we have are boxes that contain shapes. But that leads us to a problem. Is how do we contain those shapes? How do we, know that this shape is a hull and this shape is a triangle? How do we do that? Sorry about that. So here's where inheritance can kind of help us out here. If we go ahead and say that we have some, let's go ahead and get rid of this picture, or this, we know what the running time is. Let's go ahead and say we have some structure. I'm just gonna use S for shorthand of structure. We have some structure geometry, and it looks like this. It's not really the boxes, those are another object. Those would be the nodes in the BVH themselves. But logically, we can say that the representation of the geometry is the box itself, because the box doesn't get created without the geometry, or the node doesn't get created without the geometry. And then we can simply say we have a structure sphere, which takes from geometry, and again, I'll just shorthand it, and we say that it's like that. So that gives us this picture. And then we can have another struct hull, which also takes from geometry. And now, in practice, hulls can be any kind of combination of hyperplanes, but for our purposes here, we'll say it looks like a little box. And so this is kind of good. Now we're getting somewhere. Now we can kind of go back in and we can reconstruct our picture a little bit. Now we kind of do have this picture on the left matching the picture up on the right. So this is good. This should solve our problem, right? Well, no, it doesn't, because we need two things. One, we need the geometrical information. We need the contact points and the normal. But not only that, we need to be able to efficiently process these containers. And while this does give us the geometric information we want, it doesn't allow us to really efficiently process. And we can kind of see why if we draw out the memory layout. So really, what we kind of have are these little nodes with geometry pointers. But that's what the computer sees. And don't even worry about object splicing for now. Just worry about, we, as the programmer, know that these aren't actually little geometry pointers to things in a geometry buffer, but they're actually hull and sphere pointers into separate buffers. So now we have a problem. Now whenever we go to process these containers, we're going to have to do all the tests, all the updates on each pair or on each combination of containers. And I mean, really, it's you do that anyways, because it's all the same at the end of the day. You're still testing all these objects. It blows up the code and it puts responsibility in places it shouldn't be. And so we kind of want a better solution than that. Now, a semi better solution that can still work with this is this buffer right here, right? Why don't we just use this buffer? Because we know that we can just reinterpret the geometry pointer as a hull when we detect that, okay, this is a hull and this is a sphere. But again, we're blowing up the code, adding in all this tracking information because we're building from geometry upward. So we don't have enough information to start with to work back and create algorithms that will handle that data without putting a bunch of edge cases in and checking in it. We can't get around that problem regardless. And really, what we are going to end up using, we are going to end up using this and kind of sort of a combination of inheritance, but we're going to flip the problem on its head a little. Rather than start with some geometry that kind of binds everything together, right? We still need this nexus point between the uh, the geometry, so like sphere, hole. We still need that glue between this and the BVH and just general processing. And we also want a nice memory layout because cache rules. So we have some question marks. We have a question mark of what is this thing? And then also, what is the memory layout? Well, as I said before, we're going to kind of want to lean into this buffer of things. We have a sphere here, a sphere here. A hole is huge, so it takes up some more memory. Then we have a sphere here. We still want that. But we also want to be able to keep it all in one container and just say uh, mid phase this container, broad phase this container, narrow phase update. Just very, very simple, clean, clean code, right? Completely different thing here. But that's ideally what we want. And so really we're kind of creating the same picture. It's just we're putting responsibility in different places, which allows us to build a better foundation. So all that error checking and offset, not error checking, but offsetting and typecasting, we can wrap all of that stuff into a collider here and then say our BVH nodes, they don't have geometry pointers. Geometry is just a concept now. It's implicitly defined. What we really have is this collider, and we could have called the collider geometry, but it just makes more sense because we're building up to the collider now. Because we want the collider to take on the responsibility of being able to be processed efficiently and have an efficient memory layout, as well as, not to mention, if you really get into it, once you start to build out the BVH and you use the inheritance, you actually see that you need multiple BVHs because you'll start to type splice and you don't have well, maybe not, but long story short, you create all these problems that have to be solved one way or another. You can't get around those problems. But when you kind of combine it all into this top level collider structure, it really solves the problem when we compose it all together rather than inherit. And so that's enough theory for now. I will jump into the code in a part 2 to this video and show you how to actually implement this and start to build it out. Thank you all for your time, and I will see you soon.